Here we'd like to examine the phenomenon called back EMF. So we should think about what we learned about DC motors previously. We want to go further with that and combine the ideas of a DC motor with the phenomenon of magnetic induction. So why would a back EMF occur? Well, what we said with DC motors was that when a current flowed in a magnetic field, that caused there to be forces on the wires according to the right-hand rule. The force on this side of the loop would be down, and the force on this side would be up according to what we had looked at in the past. In this position, if the loop is at rest, then there's no reason for there to be an induced current or an induced EMF in the loop. But what if the loop is moving? We didn't analyze that situation in regards to induction. So, if our loop is rotating clockwise currently, that would mean these wires are moving in the directions of the green arrows now. So let's say, just for a moment, that those are the velocity vectors of those wires. Since we have wires moving in a magnetic field, there can be an induced EMF. And in which direction would it be? To figure out which direction the induced EMF would be, we should use the right-hand rule for wires moving in magnetic fields. So point your pointer finger in the direction of motion of the right side of this loop. Then your middle finger can point in the direction of the B field, and the thumb will point in the direction of the induced current or induced EMF. So this is V, the pointer. This is the middle finger, and that's the direction of the B field. And over here is the thumb, which will be the direction of the force on the positive charges. So what would this do? Well, that direction actually goes against the direction of current, and that's why it's called a back EMF. We have an EMF of the battery in the DC motor, but we're also now going to have an EMF that opposes the battery. The way that we'll draw that is we can have an EMF of our battery that wants to push current in a certain direction around the circuit. But now what we can also have is a back EMF. In this position, the velocity of the wire is actually in the same direction as B. So interestingly, there will be no back EMF when the loop is perpendicular with the field. So here we have a back EMF, and here we don't. The back EMF then is going to be oscillating and changing in the same kind of way that an alternating current does. It can do it very rapidly as the rotor spins in the DC motor. The faster the rotor is going, the more back EMF we'll have. This diagram shows an example of a DC motor that has an EMF of its battery making current want to flow a certain way through the rotor. and then there's a back EMF created that opposes it. The back EMF occurs anytime the rotor of the motor is moving in a perpendicular way through the magnetic field. Initially, when the loop of the DC motor is stationary, there'll be no back EMF. However, the more the motor speeds up, the more often the charges of the wire will be cutting across the magnetic field lines. This motion will induce an EMF which tends to oppose the DC battery's EMF. So just for a simple example of this, let's say that the EMF of a battery is 100 volts. And there's a resistance of the motor coils 10 ohms. When the motor is at its normal operating speed, the back EMF generated will be 80 volts RMS. So what is the initial current in the motor? To get the initial current, we'll just assume that there's no back EMF at that time because the rotor isn't moving. So all we want to do is use I. The current is the voltage divided by the resistance of the motor. And so that starting current can actually be pretty high in many cases. And oftentimes the design of the motor has to allow for high currents at the beginning. So here it looks like 10 amps of current initially. Now, what is the RMS current in the motor when the motor is at its normal operating speed? So for that, what we want to do is assume that there's a back EMF of 80 volts opposing the 100 volts of the battery. So what we could do is find the difference there, which would be 20 volts. And then we'll divide that by the resistance of the coil. So even though the starting current of the motor is 10 amps, once that thing gets up to its normal operating speed, the current is decreased substantially in the coil because of this back EMF phenomenon.